History of Mathematics, Lecture 25, next to the last lecture. And final exams a week from today, 8:30 in the morning in Gillette Hall, room 205. And the last topics in the course, chapters 11 and 12, were on the set theory of the great German mathematician Georg Cantor. And maybe a way to review this material and also to review for the final is for me to go over homeworks 9 and 10, which cover these two chapters. So I'll see, in fact, whether I can go through all of those two homeworks today. Any questions before we start? If not, let's look at homework 9, number 1. And number 1 is to define a one-to-one correspondence. So a one-to-one correspondence is a function, let's call it f, from a set A to a set B that has two properties. It's one-to-one and it's onto. So you have to know what these two words mean. So F1-to-1 means that if A and A prime are in the set A, the symbol means in, and A is different from A prime, then F of A is different from F of A prime. So the usual picture is, here's the set A, here's the set B. Here we have two elements, A and A prime, that are different. You have a function f from A to B, and A gets mapped to an element f of A in B, and B gets mapped to an element f of A prime in the set B. And if these two elements are different, if A is different from A prime, then these two elements are different. So what you do not have is a function that sends two different elements to the same element in the set B. That's what one-to-one means. And F is onto means that for every element B in the set B, so here's an element B in the set B, there exists at least one, could be more, at least one element A in the set A with f of A equal to B. So given any B, there's an element A in the set capital A, so that B is equal to f of A. If the function is not one-to-one, there can be more than one such element A, but to say that the function is onto means that there's at least one. And so that's what a one-to-one correspondence is. And let's actually go from that directly to problem 4. It's two sets, doesn't matter what we call them, A, B, X, Y, whatever. Two sets X and Y are equivalent if there exists a function f from the set X to Y that is a one-to-one correspondence. And equivalent means equivalent. Well, that's the definition of equivalent. It can be read as X and Y have the same number of elements, or X and Y have the same cardinality. But this is the meaning of the statement that sets the sets X and Y are equivalent. Okay. And any questions about this so far? Problems 2 and 3 are to examine or to construct particular one-to-one correspondences. So in problem 2, we're going to construct a one-to-one correspondence F from the open interval 0, 1. So this is the set of all X strictly greater than 0 and less than 1. So in set notation, we're a set of all X such that X is strictly greater than 0, strictly less than 1. And we want to find a one-to-one correspondence, or we will show that a certain function is a one-to-one correspondence from the open interval to R. And we define this function to be, or define f of x to be 1 over 1 minus x minus 1 over x. And if you put this, if you just do fractions, this is x minus 1 minus x in the numerator, that's 2x minus 1 over x times x minus x squared. So this, I mean, to be able to simplify this fraction and subtract these fractions and get this, this you can do. And we want to prove this is a one-to-one correspondence. So prove F is a one-to-one correspondence. Now, if you look at this function, you say, what is the limit of f of x as x goes to infinity? As x goes to, sorry, not as x goes to infinity, because this function is only defined between 0 and 1. What is the limit of f of x as x goes to 0? So if x goes to 0, so this is the limit as x goes to 0 of 1 over 1 minus x minus the limit as x goes to 0 of 1 over x. As x goes to 0, 1 over 1 minus x goes to 1. And as x goes to 0, 1 over x goes to infinity. So this is minus, this goes to minus infinity. So maybe I should just make it simpler like this. So we're taking the limit of this function, 1 over 1 minus x minus 1 over x. This goes to 1, this goes to minus infinity. So the limit is minus infinity. So if you look at the graph of this function from 0 to 1, what can you say? It's going to minus infinity. Like that. What is the limit of f of x as x goes to 1? That's the limit of 1 over 1 minus x minus 1 over x as x goes to 1. As x goes to 1 and from below, because x is between 0 and 1, 1 minus x is positive, but the denominator is going to 0. So the fraction is going to infinity. And 1 over x is going to 1. So this equals infinity. So this is going to plus infinity as x goes to approaches 1. And to show this function is one-to-one, it's enough to show f of x is strictly increasing on the interval from 0 to 1. Right? If it's monotonically increasing, then it's definitely one-to-one. And since it goes to plus infinity as you approach 1 and minus infinity as you approach 0, it's a one-to-one and onto mapping. So how do you show that a function is strictly increasing? So one way is calculus. You want to show the derivative is positive, because they teach you in Calc 1 that a function is increasing if its derivative is positive. So you have to take this function and differentiate it and see whether it's positive. Let's see. So we have f of x equals 2x minus 1 over x minus x squared. So you all know calculus by the quotient rule. F prime of x is the denominator squared. It's the derivative of the numerator, which is 2, times the denominator, minus the numerator, times the derivative of the denominator, which is 1 minus 2x. So this is equal to 2x minus x squared, 2x times 1 minus x. I have 2x minus 1. 1 minus 2x is minus 2x minus 1. So if I change the sign, this is plus 2x minus 1 squared over x minus x squared squared. And what can we say about this? If x is between 0 and 1, then 2x and 1 minus x are both positive. This is positive. And 2x minus 1 squared, it's a square, so it's greater than or equal to 0. And the denominator is a square, so it's greater than or equal to 0. So I have a numerator which is positive over something positive greater than 0. The derivative is positive. So that's a proof for problem 2b. Have to know calculus, and this is some calculus. There are other ways to do this, because there are always multiple ways to solve any problem, but this is one. Any questions about this? In problem 1.3, we want to construct a one-to-one correspondence between the closed intervals 3, 5, and 7, 10. So this, let's say 2, 4, 6, 8, 10. 1, 2, 3, 4, 5. We have the closed interval from 3 to 5. And we have the closed interval, this is 7, from 7 to 10. So we want to construct a one-to-one correspondence F from 3, 5 to 7, 10. Now, there are lots of functions that will do that. The simplest might be just to draw a straight line. So how do you construct a straight line that goes from 3, 5 to 7, 10? So the straight line between these, I mean, what do you need to know to construct the line? A point on the line and the slope of the line. So this straight line has slope, what? Rise over run. It goes from, 3, 7 to 5, 10. Okay. I want the line from 3, 7 to 5, 10. So the slope of this line, it's called m, is 10 minus 7 over 5 minus 3, which is 3/2. So the point slope formula, so if you have the line with slope m passing through a point x1, y1, what is the equation of that line? It's y equals m x minus x1 plus y1. So that's the point slope formula, which you use in calculus all the time. And we know m is equal to 3/2. If we take the 0.35, so if m is 3/2 and x1, y1 is 3.37, passes through the 0.37, the line is y equals 3/2 x minus 3 plus 7. Or y equals 3/2 x plus 7 minus 9/2, which is 5/2. So if I did this correctly, let's see. When x is 3, this is 9/2 plus 5/2, 14/2 or 7. When x is 5, this is 15/2 plus 5, 20/2, which is 10. So this is one example, the simplest perhaps, of a one-to-one correspondence between these two intervals. Okay. Any questions about that?
Yeah, the point slope formula, you have y equals m over x minus
No,
x1.
this is parenthesis. M times x minus x1 plus y1. This is the point slope formula.
Oh, okay.
So in this case, m is 3/2, x1 is 3, y1 is 7. I could have picked the point 510. I mean, I didn't have to pick 3, 7. I could have picked 510. In that case, you would get y is equal to 3/2 x minus 5 plus 10, which is 3/2 x minus 15/2 plus 10 is 5/2. Well, there's only one line. It's exactly the same line. It doesn't matter which point on the line you pick. So whether I pick this point or some point in between, it would be fine.
So you see how they you can also express it as y minus y1 equals blah blah m.
Yeah, it's the equivalent.
Then
But
you could change the equation however you want, divide everything inside. So which one would be like the standard point slope formula?
whichever one you prefer, they're exactly the same, right? I mean, what you're saying is, I could write this as y minus y1 equals m times x minus x1. Or I
Yeah.
could write this as m equals y minus y1 over x minus x1. These are all, they're exactly the same. They're written slightly differently, but they're the same formula. And they all give exactly the same answer. But generally, you like to put your answer in the form y equals mx plus b. So that's why I put it in this form. No matter which of these forms you pick, and no matter, there's only one slope, but there are infinitely many points on the line you could choose. And no matter what point on the line you choose for x1, y1, you're still going to get the same answer, which is exactly this.
So when it was originated, which one was the first one that they used?
I have no idea. I mean, I don't know if it was originated. It's not like this is a complicated thing. It's, I mean, there's no original formula. I mean, I don't know. I have no idea how old this is. It could go back hundreds of years. And when it's, you see it in pre-calculus, you could say, well, you could start with this to derive this. I mean, there are any number of ways you can do it. There's no original formula, but they're equal, they're equivalent. It's like saying, 6/3 is the same as 10/5 is the same as 2. the different ways of writing the same number, and you can't say one's better than another, they're equivalent. These are the same formula written in different ways. Because there's only one line. No matter what you do, there's only one line. Does that make sense?
Yeah, I get it.
Okay. Here's another one-to-one correspondence. This was problem number 6. You have the odd positive integers and the even positive integers. And we want to show that they are equivalent sets by constructing a one-to-one correspondence between them. So you can divide f, well, the easiest way, I guess, from f from odd to even is that f of n is n plus 1. I guess that's the simplest. There are other ways you can do it, of course. Because you add 1 to 1, you get 2. Add 1 to 3, you get 4. Add 1 to 5, you get 7. Or if you want to write, so this is for n odd. If you want to write f of an odd number as 2k minus 1, then f of 2k minus 1 would be 2k. That's like the simplest thing you can do. This is for all k greater than or equal to 1. Let's look at number 8, actually, since I'm constructing these things. We take n to be the natural numbers or the positive integers, and n squared to be the ordered pairs of positive integers, all a, b, where a and b are positive integers. And I want to show these have the same number of elements. So I want to construct a function f from n to n squared, which is a one-to-one correspondence. So I can show you one way to do this by drawing a picture. So, I mean, this will be the method. So what are the points? This is 0, 1, 2, 3, 4, 1, 2, 3, 4. So the points with positive integer coordinates, so they don't lie on the x or the y axes, but it's these points. These are the first few. And so on, goes on forever. So I could enumerate these points. First, I'll show you the method. It's like, start with this point, and then look at these sort of diagonal lines. And you should sort of see that every point lies on one of these lines. Right? As you draw these diagonal lines, you get every point. So let's say this, we assign to the number 1 this point. And to this point, we assign 2, 3. Just start at the bottom and work your way up. See, if you look at, see, this point is coordinates 3, 1, 2, 2, 1, 3. On any given line, if you extended this line, if we were to hit at 0, if this were the point n0, then when you go over 1, this would be n minus 1, 1. When you go over and up 1, this would be n minus 2, 2, and so forth. The n minus 3, 3. The sum of the coordinates of all these points add up to n. So in any one of these diagonal lines, on each diagonal line, the coordinates of the point A, B have the same sum. So in any case, just from this picture and this description, this is a one-to-one correspondence between the positive integers and these what are called lattice points in the first quadrant, the points with positive integral coordinates. And you can actually give a formula for this, but that would take us too far afield. But there is actually a very nice formula that exactly describes this function. That's problem 8. Oh, and then problem 9 says to look at the linear equations ax plus b with ab in N2. So all of these expressions, well, the number of these expressions is just the number of ordered pairs, AB with A and B positive integers. And the number of ordered pairs is the same as the number of positive integers. This is equivalent to the set N. That's what we proved in the previous problem. So 8 implies 9 immediately. We're just looking at AX expressions, AX plus B, and there's 1 for every ordered pair. Let's go to what is the most important parts of this homework, which are problems 5 and 7. So in problem 5, we say that the set X is denumerable or countably infinite if X is equivalent to the positive integers. That is, there's a one-to-one correspondence between X and the positive integers, and the cardinality of X, or the number of elements of X, is always denoted in this book by X with a bar over it, and we call that Aleph naught. GHT, Aleph naught. So Aleph naught is the number of elements, it's the number of positive integers, or the number of any set which is equivalent to the positive integers, or any set which is denumerable or countably infinite. So a set is countable, denumerable, countably infinite, if it can be put in one-to-one correspondence with the positive integers. And recall that cardinality of a set X is less than or equal to the cardinality of a set Y if there exists a function f from X to Y that is one-to-one. Not a one-to-one correspondence necessarily, but one-to-one. And we say that the cardinality of X is strictly less than Y if cardinality is less than or equal to Y and not equal to Y. So this is what it means to say that one set is less than or equal to the number of elements of another set, or that one set has strictly fewer elements than another set. And X is uncountable if the number of elements in X is greater than or equal to Aleph naught and not equal, or is strictly bigger than Aleph naught. or strictly bigger than the number of positive integers. That's what it means to be uncountable. An uncountable set is infinite, but cannot be put in one-to-one correspondence with the positive integers. And the great theorem in chapter 11 says, if we let C, or if we take the open interval from 0 to 1, this set is uncountable. There are infinitely many numbers between 0 and 1, but they cannot be put in one-to-one correspondence with the positive integers. And the proof is by contradiction. And we use the fact that every number x between 0 and 1 has a unique decimal representation, infinite decimal representation, which is not all nines eventually. Good. We know some numbers, like if you have a half, you can write it as 0.49999. It's all nines eventually, or 0.5000. So these are the only numbers that have two different decimal representations are ones which end in either all zeros or all nines, and you can so just choose one, and for simplicity, let's just choose the one which is all zeros. And so the proof of Cantor's theorem is by contradiction. This is contradiction. By contradiction. Assume you can list a countably infinite list. Assume there is an enumeration of the real numbers from 0 to 1. That is, there's a first one, a second one, a third one, a fourth one, a fifth one, and so forth. And in this list, which is indexed by the positive integers, every number from 0 to 1 occurs. So each of these has a decimal representation. This is a A11, A12, A13, and so on. A21, A22, A23, and so on. A31, A32, A33, and so on. You would just keep going. A1N, A2N, A3N, XN would be 0.AN1, AN2, AN3, up to ANN, and so forth. You have this enumeration. So we'll show this is impossible. So we make it's a proof by contradiction. Assume you can enumerate the real numbers between 0 and 1. Here's some enumeration. And each of these has a decimal representation. And now you do also a diagonal argument. Go down the diagonal in this array of numbers. Look at the first number, the first digit in the first number, second digit in the second number, third digit in the third number, fourth digit in the fourth number, so on, the nth digit in the nth number. Look at this sequence of digits and define a number y with decimal representations B1, B2, B3, and so forth in 0, 1 as follows. Let B1 be any number different from A11, and just to make things simple, and not 0 or 9, because you have 10 choices for a digit, so never choose 0 or 9. So let B1 be any number different from A11. B2, any number different from A22. B3 be any digit not equal to A33 in general, the nth digit you pick Bn is going to be different from A and N, and not 0 and 9. So here we have an infinite decimal. It's an infinite decimal starting with 0 point, the integer part is 0. So this is strictly between 0 and 1. It's not 0, it's not 1. And y is different from xn for all n because they differ in their nth decimal digit, because bn is different from ann. And that's a contradiction. This is supposed to be a list of all the real numbers between 0 and 1, but I just constructed a real number between 0 and 1. It's not on the list. This is Cantor's argument. It is a beautiful, beautiful, beautiful argument. Any questions about this? There are two more problems on this set, and if I have time, I'll come back to them. But I want to make sure I also get to do the homework problems for chapter 12. So this is, oops. So there's a typo on the homework. It says homework 9. But it should be homework 10. This now is homework 10, chapter 12. So it's very important to know what the power set of a set is. So the power set of a set A is the set of all subsets of A. And it's denoted by a script P of A. So this is all the subsets of A. And this includes A is a subset of A. So A is in the power set of A. And the empty set is a subset of A. So the empty set is in the power set of A. So this symbol, this is called the empty set, which is the set that contains nothing. So if you want to think of a set as a suitcase where you put stuff in the suitcase, and the set is what's in the suitcase. If the suitcase is empty, then it contains the empty set. And as an example, if you take the set A, consisting of 3 elements, the number 4, the letter H, and the Greek letter pi. So the cardinality of A is 3, right? There are 3 elements in the set. And how many, and what's in the power set? So what are the subsets of A? So you have, of course, the empty set. You have the 1 element sets, the set containing just 4, set containing just H, set containing just pi. You have the 2 element sets. You would have the set containing 4 and H, the set containing 4 and pi, and the set containing H and pi. And then you have the subsets with 3 elements, but it's just the whole set, A. So the power set of A is a set, and these are the elements of the set. The elements of the set are subsets of the set A. And in this case, there are how many? 1, 2, 3, 4, 5, 6, 7, 8. So the power set of A in this case has 8 elements, which you might observe is 2 cubed, which you might observe is 2, and what is to the cardinality of A? Let's see what happens.
What is the one on after pi? Yeah, what's the one next one on the second one?
So these are the 1 element sets. These are the 2 element sets. So if you have 3 elements, how many 2 elements? You can take 4 and H, that's what this is, 4 and pi, or H and pi. These are the 2 element sets. These are the 1 element sets. This is the 3 element set, and this is the 0 element set.
So the 3 element set only has A?
No, is A.
Oh, that means all of them. Okay.
Yeah, A is this. This is the same as writing 4, H, and pi. That's the same.
Okay, thank you.
And in fact, the next problem is to prove that if A is finite and the cardinality of A is n, then the power set of A always contains 2 to the n elements. And we're going to prove this, well, there are lots of ways to prove it. Let's look at the simplest examples. Suppose n is 0. So what does it mean to say the cardinality, the number of elements of the set A is 0? It means A is the empty set. And so what is the power set of A? Well, the empty set has only one subset, the empty set. So if n is 0, the power set of A has 1 element, which you'll notice is 2 to the 0. So this formula works when n is 0. Suppose n is 1. So then A contains just 1 element, A1. And what is the power set of A? Well, you only have the empty set or A itself. So the power set of A has 2 elements, which is 2 to the first power, right? So if n is 1, the power set of A is 2 to the first power. So this formula is true for n equals 0 and 1. Let me do the next sort of baby case.
Can I see the other page, please? I'm just going to share it. Can I see the bottom? Okay.
If there's just 1 element in the set, the only subsets are the empty set and the set itself. So there are 2 elements in the power set. So if n is 1, the power set is 2 to the 1 or 2, which is exactly what we see there. Suppose we have n equals 2. So the set A contains 2 distinct elements, A1 different from A2. And what are the subsets of A? You have the empty set. There are 2 different one-element sets. The set that contains only A1, the set that contains only A2, and then there's the 1 2-element set that contains both of them, which is just the set A. And how many sets are in the power set? 1, 2, 3, 4. So if n is 2, cardinality of A, which is n is 2, then the power set of A has 4 elements, which is 2 squared. And we're going to prove this in general by induction on n. So we know the statement is true for n equals 0, 1, and 2. I just wrote down the cases. So assume that it's true that if the cardinality of A, is n, then the cardinality of the power set of A is 2 to the n. And I must prove this for n plus 1. You have a set A that has n plus 1 elements. So suppose A contains n plus 1 different elements. So I want to divide the subsets of A into 2 classes. Subsets B of A. So we have B contained in A. B is a subset. So B is in the power set of A. That means B is contained in A. And either this last element, AN plus 1, is not in B, or it is in B. Right? Every subset of A either contains this last element or it doesn't. Some subsets B don't contain that last element, some subsets B do. So let's count how many elements satisfy each of these 2 conditions. If AN plus, so we have AN plus 1 is not in B, is the same as saying that B is a subset of just the first n elements. Because B is a subset but doesn't contain this, so it has to be a subset of A1 up to AN. So AN plus 1 is not in B if and only if B is contained in this, and the number of such B is exactly the number of subsets of an n element set, which is 2 to the n. The number of subsets of A1 up to AN is 2 to the n. That's the induction hypothesis. Suppose AN plus 1 is in B. That means B is written as AN plus 1 union some set B prime. And B prime is a subset of A1 up to AN. AN plus 1 is in B. If you take away the AN plus 1, what's left is a subset of A1 up to AN. But again, this is a subset of an n element set. So the number of B prime that you can pick is also 2 to the n. So the power set of this set A consists of the sets that don't contain AN plus 1, there are 2 to the n of them, plus the sets that do, which is another 2 to the n. So that's 2 times 2 to the n, or 2 to the n plus 1. And that's what we wanted to prove. So by induction, if every set with n elements has a power set up to the n elements, then every set with n plus 1 elements has a power set with 2 to the n plus 1 elements. That's the proof. Any questions about this? Problem 4, I already discussed, but I'll do it again. What does it mean to say that the cardinality of B is less than or equal to the cardinality of A if there is a one-to-one function f from A to B? That's what it means to say B is less than or equal to A. And to say B is strictly less than A means that B is less than or equal to A, and B and A don't have the same number of elements. So this means there's a one-to-one function from B to A, but there's no one-to-one and onto. There's no one-to-one correspondence between B. And in particular, if B is a subset of A, so here we have A, and sitting inside A is the set B, the function f from B to A, defined by f of B equals B, is one-to-one. Here you have the set B, and you send every element to itself. So if B is a subset of A, you can define a function from B to A. It's just the identity function restricted to B, f of B equals B. That's one-to-one. So if B is a subset of A, then the cardinality of B is less than or equal to the cardinality of A. So all of this is a kind of review, if you like, but it's important then, if you're seeing it as you likely are for the first time, because you haven't taken a huge number of mathematics classes where this might have come up, then it's very important. That's very nice. So what is the great theorem in chapter 12? It says that for every set A, finite or infinite, the cardinality of A is strictly less than the cardinality of the power set of A. So this is really important. This says that if you take an infinite set, there's a strictly bigger infinite set. So you have an infinite number, and then the power set of a set with that number of elements is an even bigger infinite number. And you repeat this over and over again And you get an infinite number of infinite numbers that are all different, one bigger than the next. And we prove this. This is the second great theorem of Cantor. And Cantor's proof is a kind of diagonal argument, not exactly a diagonal argument, but a kind of a diagonal argument. So how do we show that this is less than this? So we must show that the cardinality of A is less than or equal to the cardinality of the power set of A, and that the cardinality of A is not the same as the cardinality of the power set of A. So the two things you have to prove to show strict inequality. To show that the cardinality of A is less than or equal to the power set of A is easy. Define a function f from A to the power set of A by f of the element little a is the subset of A consisting of just that one element. So A is an element of the set A, and if you take the set containing only A, that's a subset of A. This is a subset of A, so it's in the power set of A. And every element of A gets sent to a different subset of A. So this function is 1-to-1. So you might have to think about this for a little bit, but this is a 1-to-1 function from the set A to the power set of A. And
Professor,
because
is
there
this still number 5 or are we on number 6?
This is problem 6. This is the great theorem in chapter 12, and this is the proof. This is the proof of the great theorem. So if I take an element of A and I look at the subset of the set capital A consisting of just that one element, that defines a 1-to-1 function from the set A to the power set of the set A. And because there exists such a 1-to-1 function, this means the cardinality of A is less than or equal to the cardinality of the power set of A. So this half is done. And what I have to show is that these two numbers are different, or in other words, that A is not equivalent to the power set of A. So must show this is false. And the way we're going to show this is false is, again, by contradiction. We'll assume that it's true and get a contradiction from that. So let's assume A and the power set of A are equivalent sets. This means that we're assuming there exists a 1-to-1 correspondence F from A to the power set of A. So we have the elements of A, and we have the elements of the power set of A, which are subsets of A. So A, B, C, D, and so forth. And we have this one-to-one function from F to the subsets of A. So the example, just a make-believe example, but so let's say that A gets sent to the set consisting of B and C. B gets sent to, let's say, a set consisting of D. C gets sent to a set consisting of A, B, C, and D, and so forth. So to every element of A is assigned a subset of A. And we're assuming that this assignment, this function F, is one-to-one and onto. So every subset, of A is on this list. It's one of these sets. And we're going to assume that leads to a contradiction. So I want to define a subset B of A as follows. An element A in A, so that A be in A, then we say that A is in the set B. A is an element of B if A is not in F of A. That is, for every element A, we're assigned some subset F of A. Right? So A is an element of the set A. F of A is a subset of A. It may or may not contain the element A. So look at all the A's, elements A in the set A, for which A is not in F of A. And that defines a subset of A. So B is a subset of A. So B is in the power set of A. Right? So because B is in the power set of A, this implies there exists some element Y in A with F of Y equal to B. So over here we have some set B, and there has to be a set element Y which gets sent to B. I've constructed a subset B of the set A, so it has to be that there's an element Y in A such that F of Y is B. And then we ask the question, is Y in B or not? Because B is a subset, Y is an element. Either Y is in B or Y is not in B. So let's analyze this. If Y is in B, then Y is in F of Y, which is equal to B. But if Y is in F of Y, then Y is not in B. Because B consists of all the elements A, where F of A is not in B. So if F of A is in B, if F of A, sorry, B consists of all the elements A, such that A is not in F of A. So if Y is in F of Y, then Y is not in B. But this is a contradiction. We're saying that if Y is in B, then Y is in F of Y, because F of Y is equal to B. But if y is in f of y, then y is not in B. So somehow, if y is in B, then it's not in B, which is ridiculous. That's a contradiction. So therefore, it has to be that y is not in B, which means y is not in f of y, because f of y is equal to B. But if y is not in f of y, then y is in B. So we have, again, another contradiction. If y is not in B, then it is in B. But these are the only two possibilities. Y is either in B or not in B, but both of them are impossible. So our assumption had to be false. And the assumption was that A was equivalent to the power set of A. So that's not true. So therefore, cardinality of A is not equal to the cardinality of the power set of A, which means the cardinality of A is strictly less than the cardinality of the power set of A. That, again, for, I don't know, second or third or fourth time, is the proof of the great theorem in chapter 12. Any questions about this? Let's see. It's worth spending a few minutes looking at this proof because it really is kind of a basic thing.
What symbol do you use for equivalent?
Um, A equivalent to B, just use the squiggle,
So what's how would
which is the same as saying that the number of elements of A is the same as the number of elements of B. So either of these can be used.
if you put two squiggles, that's approximate, right?
That's yeah. So in calculus, for example, you might say this is it can mean lots of different things, but it's often used to mean approximate in some sense. Whatever approximate means, that's true.
And what about similar and congruent to?
Well, so in geometry, this is usually used for similar in geometry, and congruent is often written like that. In algebra, this means isomorphic. I mean, there are a lot of concepts. There are more concepts in mathematics than there are symbols. So the symbol depends on the context. If you're talking about set theory and cardinality of sets, this means the two sets are equivalent or have the same number of elements. If you're talking geometry and you use that symbol, it usually means similar. So one square is similar to another square. Right. It's just a different use of the same symbol, right? So you have to know what subject you're engaged in.
You're gonna be available tonight, right?
Yes, 7 o'clock.
Okay.
And we have class on Wednesday, but that class is entirely for answering any questions you have on the whole course.
Did you upload it review for the final?
I'll do that, I think a few minutes after class ends.
Okay.
But the best review are the homework problems. Yeah. And I mean, I actually have a review here, but the view is mostly just a collection of homework problems. So, but I will post it. But the homework is really the best review. Anything else that I should talk about today? There are a couple of problems I didn't go over, but they're less important than what I did go over. And I tried to pick out the types of problems that might appear on the final exam. If there's nothing else, then we will quit for the morning. So if you have questions, again, I have Zoom sessions tonight, tomorrow night, Wednesday night, and I'm not available Friday or Saturday, but if you have last minute questions, I can have a session on Sunday also if you're interested. Okay. All right. Be well, all. See you Wednesday.
All right, thank you, Professor.
Good night. Good night. Bye-bye.